on here.
Yeah. And everything on there is on the text. It works both directions.
I have the road for this.
Well, no, that's the trouble with the textbook. I mean, they have more time to put a lot more stuff in. You sometimes I'll cover a little bit more than the book does, but some other times the book will cover more.
In English, they put in weird words like so.
Yeah, weird words too. Yeah, and as I said before, you read the textbook, and every time you read it, the same words in the same order. Whereas at least if you ask me a question, I can answer it slightly differently the next time. No, it's a different answer, but I mean, say it a little bit differently so it might make sense. And if the words are, I mean, I love those big words, but if they don't make sense to you, you can say, hey, I don't really understand that.
That's what you're here for.
Yeah.
That's what you're here
Yes,
for.
exactly. Try to make sense out of this stuff. Look, I wanted to finish up on enzymes. We started talking about enzymes, but I want you to realize how important enzymes are, what they're doing, and all that. And if you recall, I have said several times my unpoetic view of a cell, statement about a cell, is that it's a bag of chemical reactions. Because that's what's happening. Any one moment cells in a cell, there are hundreds, thousands probably of chemical reactions occurring. Those reactions, these organic reactions, they don't occur at such a low temperature at all easily. Low temperature meaning our body temperature. That's a low temperature for most of those organic kinds of reactions. They're much happier, meaning that they'd rather work at much higher temperatures, way higher than our body temperature. So if we're going to get any of those things to work, we have to have some way to force those reactions to work. And that's where the enzymes come in. And first of all, what are enzymes made of? They're proteins, yes. And remember I said that maybe, my guess is that maybe half of all the proteins we make are enzymes. It's a guess. It could be more than half. I have no idea. But certainly a large percentage of all the proteins we make are enzymes. There are a lot of other functions of proteins, remember. Proteins are the worker molecules. So they've got a lot of functions, but I'd say think at least half of the proteins we make are enzymes. And I said these are biological catalysts. And what's a catalyst? A catalyst is something that will speed up a reaction. Catalysts speed up reactions. And they're not used up in the process, so they can be used over and over and over and over again. Okay, speed up reactions and are not used up. RXN, I've used that before, I think, for my abbreviation for reaction. So, but catalysts, there are all kinds of catalysts, such as in your car, you have catalysts in your catalytic converters, right? And the catalytic converter, it's got catalysts that are probably palladium molecules, or platinum molecules or something, but it's trying to convert various gases that they don't want out there to gases that aren't so bad. Yeah. So there are all kinds of things that can act as catalysts or whatever, but enzymes, these are biological catalysts, meaning that they are going to catalyze chemical reactions, biological reactions in your cells. And as I said, every single reaction in a cell, or even outside the cell, well, it doesn't really matter. But every single reaction, every single biological reaction has some specific enzyme to allow that reaction to work. Okay? So this is important. It's an important idea that every chemical, biological reaction is taking place. Every biological reaction has some specific enzyme to catalyze it, or I'll just say to allow it to work. Or you can say to catalyze it, whatever. I mean, it's the same thing here, okay? And again, keep in mind that 37 degrees centigrade, our temperature is a really low temperature for these kinds of reactions. Now, just to remind you, reactions, most of these reactions are forming covalent bonds or maybe breaking covalent bonds. Well, let's just talk about forming covalent bonds. What's a covalent bond? It's going to be on the example.
It's when two nucleuses share, or
Two-
one
two
electron,
atoms.
two atoms share the same
Pair
pair
of
of
electrons.
electrons.
Right.
Yeah.
So a covalent bond is two atoms sharing a pair of electrons. Well, now here's an atom. They've got their valence electrons floating around, and how is it that you're going to form this? And what it amounts to is you have to have, and remember, molecules are in motion, just normal molecular motion. But if this particular, whatever the atom is, and this particular atom happen to be moving towards each other at the right speed and the right orientation so that they come together like this, and then there's this reorientation of the valence electrons so that they can share that pair, then they will form a covalent bond. But it's a chance occurrence. Now, when you have trillions and trillions and trillions, I mean numbers beyond our imagination, of these molecules all bouncing around, occasionally they will form these bonds. Occasionally they will hit in just the right way to form these bonds. The higher the temperature, the faster they're moving, so the higher the chance of forming these bonds. But we don't have the luxury of just raising the temperature of our cells to have this happen. But that's where the enzymes come in. They are, because of the way they're made, they will increase the chances of forming these bonds multiple times, essentially making it practical. And the usual picture that we draw of an enzyme, and they draw it like this because they're more or less shaped like this. Most proteins are globular. Not all. Some proteins are fibrous, but most of them are globular. And so these are globular kinds of molecules. This is 2 dimensions, but 3 dimensions is what we want. Yeah.
Does that say RX in?
Yeah, just for reaction. It's just my abbreviation for reaction. It's not I didn't invent it. It's a common abbreviation for reaction.
So those are prescription drugs or nurses?
Try to use abbreviations when I can, just because I don't have to write all the words out. But so anyway, but the point about these globular molecules, they have this little indentation, and that little indentation is called the active site. And it's called the active site because that's where the reaction occurs. And so, I just made this up last time. I said, what if you have A plus B going to C? Whatever A and B are, it doesn't really matter. Whatever C is, it doesn't matter. Just some 2 molecules that are joined together, forming some kind of a bond. So now that it's probably covalent bond, so now it's the C molecule. Well, again, these guys are just bouncing around. But if there are enzymes, and of course there'll be many more than just one enzyme for this reaction in your cell. There could be thousands of that same enzyme in your cell. But there's a place where A can bind and a place where B can bind, and it's only A can bind in that one spot, only B can bind. It's a temporary binding, okay? But by binding together, I'll give myself a little more room. I just make that big enough. Let's make it a little smaller. Okay, so here's A, here's B. Okay, but when they bind together, when A and B both bind, that'll cause the enzyme to shift a little bit in this shape, and it'll actually close a little bit, which will bring A and B closer together in just the right orientation that the chances of forming the bond are very, very high, forming that covalent bond. Okay, so A and B join, the molecule changes shape just a little bit, bringing A and B closer together, and then these guys will be given off as C. No longer we have A and B separately, you have C now. But then that opens us up for another A and B to join, okay? And we can get another C forming. And it just goes on and on and on, and the reaction time is very quick. Most enzymes, can catalyze thousands of reactions every second. These are, we can't conceive of this kind of thing happening, because this is at the molecular level. But, so, each enzyme can just be cranking out whatever the C molecule is, you know what I'm saying? That makes sense. So it's very, so the enzymes are incredibly important. Actually, I shouldn't say make it stronger. They're absolutely necessary for cells, because they wouldn't be able to have all these reactions occur without them. So does that make sense about enzymes, how important they are?
What is that why they're biological?
They're biological because they are proteins. That's a biological molecule. And they're catalysts, but they're catalysts for biological reactions. Actually, they've been trying to. In fact, I think kinds of enzymes to catalyze certain kinds of reactions. I don't know. They're getting very sophisticated these days with making all kinds of molecules. I don't know what they've done in terms of trying to
Use
take
enzyme.
enzymes and modify them so they can maybe catalyze something else. I don't know.
Because that's a really brilliant
Pretty
idea
wild.
to do it.
The other thing is that some enzymes, I'm not just talking about this, some enzymes have what are called regulatory sites. And the proper word for that is allosteric site. Now, those are fancy words, okay? Allosteric. The word steric refers to just the shape of it. The allos refers to, it means other. All it means is other. So it means there's another site on this other than the active site. So the active site, let's actually define this. I guess I didn't officially define it, so let's do it. The active site is where the reaction occurs. Where the reaction, whatever the reaction that it catalyzes, where the reaction is catalyzed. And that, calling it the active site makes sense. That's where all the activity is. That's what where the enzyme is doing what it's supposed to be doing. The allosteric site is just some other site on that molecule, but it's a regulatory site. It's a regulatory site that can turn on the enzyme or turn off the enzyme. Most enzymes don't have this. Most enzymes are just constantly there and doing what they're doing. But some enzymes, once you've made enough of whatever the product is, the enzyme is turned off. And then when you start running out of whatever that product is, the enzyme is turned on again. Sort of, it's a feedback kind of system. And it's like your central heating at home. You set the central heating, we'll say you set it for 70 degrees. And if it's below 70 degrees, click, it'll turn on and the heat will come out and the temperature gets, let's say it's 60 degrees in your house, it goes 60, 62, 64, might get up to 70, maybe get up to 71, click, turns off. Okay? So then your house is at that temperature, but it starts cooling off, 69, kicks on again, and then, you stay at some kind of even temperature. So it's it's regulated. Well, that's the way some enzymes are. So for example, let's just say there's some system where you have A plus B going to make C, and then C, you get C plus D is going to make we'll say E, okay? Just making up something. There's no particular thing. And each of these arrows, well, this would be one. This is just a continuation. But for each of these arrows, then, would be some enzyme. There'd be some enzyme. We'll say here's enzyme 1, here's enzyme 2. So enzyme 1 will catalyze A plus B making C. And then once you have some C's, they'll get together with some D's, and enzyme 2 will make E out of it, okay? All right, so, but let's say from your cell's perspective, you only need a certain amount of E. And once you've made enough E, you don't need any more. Well, what might happen then is that enzyme 1 might have an allosteric site. Okay, this might have an allosteric site. And so you start, A and B start forming C, then C and D start forming E, and so E starts to build up in your cell. But once you get to a certain amount of E, it turns off this enzyme 1, so you stop forming C. Once you stop forming C, you'll stop forming E. You know what I'm saying? So an allosteric, so take this reaction. So, well, let me give you an idea of what the allosteric site looks like. So here's your enzyme like this. There's the active site. I'm going to put a little kind of thing like this. So here's the active site right here. The normal kind of active site that we had before, where A and B are going to join together, say, to form C. But then there's another site, and this will be the allosteric site. And usually, not always, but usually that site, what fits into that site which binds that site, is whatever the end product is that you're trying to regulate. How much of the E, for example, is in there. So if E is what you want to regulate, say this is the one that you need a certain amount, but not too much, but not too little. It may be that E fits into here. And so as you start building up more E and more E, some of those E's will fit into this site right here, the allosteric site, and then that will change the shape of the molecule so that A and B can't fit into here anymore. That makes sense. And so if A and B can't fit into there, or if they fit in, they can't get close enough to react.
What changes the shape of it?
The actual, whatever this end product is, in this case we're saying is E that we want, but only so much, we don't want too much. But as you start building it up, some of those E molecules are doing whatever they're doing in your cell, but some of them will hook into the allosteric side of enzyme 1.
Which tells them to stop producing.
Enzyme 1. And when it fits into this allosteric site, it'll change the shape of the enzyme, so either A and B can't fit, or if they do fit, they can't react.
So something goes into allosteric, it can change the whole shape.
Yes, it can prevent, then it can prevent the enzyme from actually doing this thing. So if you take this reaction, so we'll take this A and B, forming C, and enzyme 1 is catalyzing that. C and D gets together, and then enzyme 2 is going to catalyze to make E. So we're saying that in our case, our enzyme that has the allosteric site, it is going to react with E. The allosteric site react with that last product, E. Now, let me just write this down, and then I want to answer your questions here. Let me just do this. So we'll say, again, take this reaction as E builds up in the cell. Whatever E is, I mean, it's going to do whatever it does because it's some product. But as E builds up in the cell, some of it binds to the allosteric site.
Is that just because it's open?
Well, because the allosteric site is open.
Yeah.
But yes, that's absolutely true. And see, again, remember I said the universe runs on statistics.
Yeah.
It's all a statistical phenomenon because you have thousands of enzyme 1. You're making E. You're probably making many thousands of copies of E, and the E is doing whatever it's doing. But some of those E molecules are going to hook into this allosteric site.
Yeah, because you would figure once.
The more E's you have, the more E's will be sticking into these sites just because, statistics.
Yeah, once you reach the optimal level, the excess available E starts to attach itself and shut. That's like a shutoff valve. Yeah.
Exactly what it's a shutoff valve. So some of it binds to the allosteric site on, we'll say, on enzyme 1. And
the E that's no longer utilized attaches.
I'll just say it's working. Now, as E gets used up in the cell, and the amount of E goes down, then
Free it from the active site.
they'll start, the binding here is a weak binding. It's not like a covalent binding, it's a weak binding. And as you start using up the E's in the cell, some of the E's start coming away from that allosteric site, and then that'll let that enzyme work. Let me write that down and I'll answer your questions. Did your question get answered yet? Okay, I'll come back to that. Let me just write this down. So, as E gets used up, the E molecules bound to the allosteric site. Away. And enzyme 1 can work again. So it's just a way to turn off an enzyme once you have enough of the whatever product it might be, or if you don't have enough, turn the enzyme back on again. But again, only some enzymes. So keep in mind, not all enzymes, only some enzymes have a regulatory site. But those that do, that adjust the cell, adjust how much of whatever it is in the cell. Now I didn't answer.
That was my question. I was just wondering how you differ which ones
It's a good question. And some are, and typically what it is, I only said A plus B going to C plus B going to D. So typically it's where you have, several reactions in a row, and it's usually the last thing, whatever the last thing is the one that's being regulated. So, because a lot of times, for example, C, it may be the case that the only function C has in the cell is to react with D to make E. It may have no other functions in the cell, see? So, but why keep on making C and making C and making C if we're not going to be making E? That's all we really want C for. But you can turn off making C once you get enough of what you really want, And then once you run out of this, then you start this whole process again. So it's a neat way to regulate how much. Yeah.
So in the same sense that once you've made enough C, the excess C would find the allosteric site, enter it, and then stop the production of
You take
C?
C, if there is an allosteric site that binds to C, it just depends.
Okay.
Usually it's the end product
That has the
has
allosteric.
there's some earlier enzyme that has an allosteric. Sometimes it's its own enzyme, the one that just made it. Sometimes it's that. I mean, there's no rule.
Okay.
It's just again on the average. Yeah.
So to clarify the bottom that you just wrote.
So let me say it makes maybe a little clearer about it better. We're hypothesizing that E is whatever it is that the cell needs, but not too much, not too little. You need some amount of E.
Okay.
So you start out by making E in this reaction, but once you get enough of the E, then you start making extra E's. They start binding to that enzyme, and they stop any more production. But whatever E is in your cell, it starts to be used and gets used, and you're using it up. So the amount of E in your cell is starting to run out. And then you still always have some, you had some of these E's bound here, but they're weakly bound. When you have a lot of E's, then a bunch will bind here. When you don't have too many E's out here, hey, these will come away and they're not as likely to be bound there. So you run out of E, these kind of come away, and then this enzyme turns on again, you start doing the whole thing over.
And it knows when to shop when there's too many E's.
It knows when, again, it's a statistical phenomenon.
Yeah.
When there's a lot of E's around, enough of them will bind to these enzymes to stop them. When there aren't very many E's around, hardly any of them will be binding to the enzyme, so they'll get turned on. Does that make some sense? I mean, again, it's just statistical, but the point about all this is that, hey, some enzymes can be regulated. Not all. I don't know what percentage, I have no idea, but some can. It's just an interesting phenomenon. It's just another level of sophistication, we might say, in terms of how enzymes work. Enzymes are very sophisticated, just for your knowledge. They're very sophisticated.
So once they're full, the barrel overflows and attaches.
All right, now look,
the thing is.
the real main part of the lecture was all this stuff. And some of this gets to be sort of heavy duty, but I'm not having you memorize a bunch of reactions. Typically, what people do is they have you memorize a bunch of reactions in glycolysis or in respiration or whatever, like Krebs. That's not my point here. I could have you do that. I had to do it when I started out, but I memorized reactions without really understanding what it was all about. I'd rather have you understand what it's all about. If you ever take another class and you're going to study these things again, you go, oh, at least I understand what it's about. Now I can memorize some of the details and fit in. It's kind of the forest for the trees problem. If you memorize a bunch of reactions, it's a whole bunch of trees without understanding how that forest works, But if you can understand how the forest works, then you can start looking at individual trees and make sense of what they're doing in that forest. That analogy makes sense?
Yeah.
All right, let's talk about a few things first, a little background. First of all, I want to give you the word organic versus inorganic molecules. And this is different from the way you use organic when you go shopping and you look at organic vegetables. It's a different use of the word organic. When you talk about like organic gardening or something like that, you're talking about not using pesticides, using just whatever. I don't know. The problem is there's so many pesticides in our environment, it's hard to get pesticide-free food, but organic food is at least closer to being pesticide-free than non-organic. At any rate, that's not the use here. In the very simple definition, we were talking about in chemistry, organic molecules contain carbon. Inorganic molecules don't. In the in part just means not organic. So inorganic,
Is that really the literal difference?
yes, with a couple of exceptions that I'll give you. But yes, inorganic molecules do not contain carbon.
Huh.
That's all.
Except for so.
Except there are a couple of exceptions which I'll give you right now because I will tell you these exceptions real quickly. But here's the thing: the reason they do all this, it all has to do with really historical reasons. When chemists were studying things, I mentioned to you that they wanted to study biological stuff. So they're studying proteins and nucleic acids and all this stuff. And I told you about how they tried to make some of these molecules, biological molecules, in a test tube, and they couldn't do it. And they thought there was something magic or special or whatever about living things. And there was an idea called vitalism, that there's something, almost magic about life. Well, then, 150 years ago, the first person was able to make biological molecule in test tube, and he showed, hey, you can do it. Now, of course, they're totally sophisticated. They can do all kinds of molecules. But it's tough. They had, it's not an easy thing to do until you learn how to do it. It's not straightforward. So, because biology is complicated. That's a big deal. Biology is complicated. But it does follow all the normal laws of chemistry and physics. It's just complicated chemistry and physics. But because of that, they started naming any chemistry that you did using carbon, they started calling that organic. And anything other than carbon, we said inorganic. The exceptions, I will give you the exceptions. Carbon dioxide is not organic. Is not considered organic. It's considered inorganic. Carbon dioxide, also bicarbonate ion, is not considered organic. Carbon monoxide is not organic. Carbon monoxide is a poisonous gas, right?
Yes.
So these guys, other than that, other than those exceptions, if it has carbon in it, it's called organic. And most of the things you wear, like your clothes, they're synthetics. These are organic molecules, but they're made in a laboratory. But all the polyesters and all those other rayons and nylon and all those sorts of things, those are all organic molecules. They're all made in test tubes. They're not made. Those kinds of things weren't ever made by cells, But so organic chemistry is this enormous discipline, absolutely enormous discipline. But all it means is the chemistry of carbon. And remember, carbon. Why is carbon such a useful atom?
Because it has
biological molecules.
Because it bonds. It has
four
different electrons.
It forms, and so it is so versatile in what it can bond with. It can make all these elaborate molecules, all the kinds that make all the biological molecules we've talked about, but also now non-biological organic molecules that we use all the time in everyday life, everything from your plastic, all the plastics and things like that. Those are all organic molecules. Yeah. Well, silicon isn't right below carbon, and it's very versatile also, but not as versatile as carbon. No, I'm not sure. But it's still, but it is. And it has been hypothesized that maybe silicon could be the basis of some
life
that exists
on other
somewhere.
planets.
Yeah, maybe. It's possible. Just because it is pretty versatile. Not as versatile, but yes, it is versatile. Yeah. Lead, I don't know about. I'm not sure how, because that's a pretty big molecule, right? But if you get too big, then it's harder to form. It's more bulky, and you can't form the molecules. But I can't say no. Anyway, so just in terms of, I need to use these words because I'm going to be talking about these things when we get to fermentation, for example. So from now on, if I say it's an organic molecule that has carbon, if it's inorganic, no carbon.
Okay.
Just remembering there are a couple of exceptions.
Okay.
And you don't really usually need to worry about bicarbonate or carbon monoxide, but carbon dioxide, which is so, well, it's not that
Everywhere
in the
is
atmosphere, but
with
we're producing a lot of
CO2,
it, of
yeah.
course, as we breathe out. But anyway, just keep in mind that is, even though it's got carbon in it, it's considered inorganic, not organic. Okay, we've talked about ATP. Remember we talked about ATP as the dollar bill. I call it the dollar bill of energy.
Yeah.
System of energy in your body.
It's the currency, yeah.
And remember the idea that, and I'm going to write this up again just because I want you, it's a very important concept, that in catabolic reactions where energy is given off, let's put this down. In catabolic reactions, energy is released. This is usually the case, okay, right? Energy is released.
And anabolics are where they're stored.
And some of the energy, and some of the energy might be trapped, can be trapped, might be trapped. Or stored. I say trapped, you could think of stored, trapped by making ATP. Because what's happening to the rest of the energy? What's it coming off as? Heat. It's coming off as heat. And that's just going to go off in the atmosphere where it's lost. I mean, obviously, for warm-blooded organisms, birds and mammals, some of the heat that was given off in all those reactions keeps us at our normal temperature. But the rest of the heat we have to give away, which is why if it's too hot, we're sweating. But anyway, so in catabolic reactions, energy is released, and some of the energy might be trapped by making ATP. A lot of them we are. Now we're going to see how we can trap some of the energy. As opposed to anabolic reactions, remember these words? Catabolic means breaking down. Anabolic means synthesizing, forming, building up. Remember that I said the way to remember, we talk about bodybuilders using the anabolic steroids that help build muscle protein. That'll help you remember that's the building up of something. That requires energy. Energy is needed to make the reactions work. So ATP is used. Okay. So part of the time then, and this is true any day, probably any minute of the day, you're doing some catabolic reactions and you're making ATP, hanging on to it for right now, maybe a few minutes later, maybe an hour later, you're going to use some of that ATP to run some other reactions. Okay. Another thing I've got to talk about. This can get kind of technical. I need to talk about it so that I can explain a couple things that we need to talk about in Krebs cycle. And if you take chemistry, you'll get much more detail about this. But they talk about oxidation reduction reactions. And they talk about, but they call them often redox reactions. By the way, they talk about, hey, this is an oxidation, this is a reduction. But the idea is, anytime you have an oxidation, something's being oxidized, something's being reduced, so they have to go together. You can't just have one thing happening without the other. Okay, what are we talking about here? Let me write this down, just give you a little definition. Most biological oxidations, involve the loss of a pair of electrons. Remember, I'm going to do E minus for electrons just to make it easy. A pair, usually it happens in pairs, not always. That's why most involve the loss of a pair of electrons And often, the loss of a pair of hydrogen ions, H plus. So let me write the same kind of thing for reduction. It's just the opposite. It's the gain. And then let's talk about a couple of words. Most biological reductions are exactly the same, except it's going to gain instead of loss. Involve the gain of a pair of electrons. And often gain of a pair of hydrogens. H plus ions, hydrogen ions. So write that down. Let me just say something. I'm not going to make a big deal about these guys on the exam you're having on Thursday, except that you need to understand something about it. Make sense out of what we're talking about. First of all, these words, oxidation reduction. When they were developing all this 150 years ago, when they were doing all this chemistry, trying to make sense out of what's happening inside. Well, not only biological oxidations, you can talk about oxidations in other molecules, copper and iron and all that. They originally talked about oxidation reductions in terms of oxygen, and that's why you see the word oxidation. And they said, okay, hey, if some molecule gained oxygen, an oxygen atom or more than one, we'll just say gain an oxygen atom, it was oxidized. And if you reduce the number of oxygens, okay, then we say call it a reduction. That's where these words came from. Oxidation meant you gained oxygen, reduction meant you lost oxygen. Okay, so, but then as they developed these concepts more and more, they realized oxygen isn't always involved, and yet you get the same kind of process going. And then finally, people these are chemists who know about all this stuff, they said, look, we can do everything with respect to electrons. Okay. So now we talk about electrons, and usually we're talking about hydrogen ions at the same time. Not always, sometimes just electrons. So we're talking about hydrogens and electrons. Now, if a hydrogen ion is given off, an acid gives off a hydrogen ion, right? That's not a big deal. You learned about that in lab. Where does an acid something gives off a hydrogen ion? That can float off into the cytoplasm, into the water, into the solution. So hydrogen ions can just float away. That's fine. And the more hydrogen ions that you're producing, the more acidic, whatever it is, right? Electrons can't do that. Electrons can't just float away. Electrons can't just go off into the atmosphere. Electrons have to go from one molecule to another molecule. They have to be handed from molecule to molecule. Okay, do you see what I'm saying? They can't just be. You can't just give off an electron and have it just float away. That doesn't happen with electrons. Electrons, if you give off an electron, if you're a molecule that's giving off an electron, that's only because some other molecule is taking that electron. Do you see what I'm saying? It's got to be directly handed to it. It's not just floating away. Am I making sense? Okay, so this is an important concept. Electrons have to be transferred directly from one molecule to the next. Can't just go flying off. Okay, so electrons have to be handed from one molecule to the next. Now here's the deal. Talked about enzymes earlier. We've talked about proteins in general, and they're the worker molecules. They have all these incredible jobs they can do. Proteins can do all kinds of things because they're made of what are proteins made of? 20 different amino
acids, yeah.
It's going to be like this. Okay.
Thanks
so,
for bringing
so
that up.
proteins are made of amino acids. There are 20 different amino acids. And so you can make all kinds of incredible sizes and shapes of proteins, and they can have all kinds of functions. Everything from muscle contraction, those are muscle proteins that are actually changing shape. To catalyzing reactions, acting as enzymes, to acting as antibodies where they can attack bad molecules and the immune system can get rid of them. Okay, so proteins have incredible jobs that they can do. But there's no good, and that's because of all these 20 amino acids, there's no good amino acid that can accept electrons or give off electrons. Okay. So I'm going to put here, but no amino acids are good E- acceptors or donators. So we're going to be talking about oxidation reduction reactions where electrons are given off and something gives it off, something else grabs it. And normally you think, hey, who's going to be involved in this process? You're going to think proteins, because they're the worker molecules. But there aren't any good amino acids. There are no amino acids that are any good at accepting electrons or giving off electrons. So proteins aren't good at this process. What we need for this is some kind of molecule that is good at it. It's a molecule that we ourselves don't make. We have to get it pre-formed in our diet. So let's put this up here. So put up here. The molecules that are used as E- acceptors and donors. I said donators. That is a very good word. Let's say donors. It was a bad word, wasn't it? Sorry.
I didn't even realize it just put donors.
The molecules that are used as electron acceptors and donors are called coenzymes. The word coenzyme means it works with an enzyme. It's not itself an enzyme.
With the stuff that's in the yeast.
Things work with enzymes. But the molecule itself is not an enzyme on its own. There was a hand. Yeah. Yes.
Well, I was going to do a mnemonic to remember.
We're still doing that.
There's a mnemonic.
Oh, you're a mnemonic. What is your mnemonic? Can remember what?
It's oil rig.
Oh, yeah. Go ahead.
Oxidation, loss, reduction, heat.
Yeah. Wait, yes. Oil. This is the mnemonic. Now, mnemonics. The word mnemonic just means a memory device, so you can remember things, and so you come up with some mnemonic. Where you take the first letter of everything, you've all done that, and we'll do the oil rig so you can see how that works. It's always good if you make up your own mnemonics, and the naughtier the better, because if there's really a naughty mnemonic, you'll always remember it. Even years from now, you'll still remember the mnemonic, even if you don't remember what it stands for, but you'll remember the mnemonic you made up because it's some really naughty.
Every good boy does fine.
Yeah, but that's for music, right? That's for the
yeah.
the notes on it.
And face.
That's and face, F-A-C-E. So yeah, so this one is, you're right. Oil rig. Let's do these.
Every acid gets busted eventually.
O-I-L-R-I-G. So what is it? It's oxidation.
E-A-D-G.
What is the loss? Is that what that stands for? Reduction is the gain. So oxidation is the loss of electrons. Reduction is the gain of electrons. So remember this electrons. So that's a good one if you want to remember it that way. It's good. I always had a pretty good memory. I still do, despite the fact that I'm kind of ancient. But I always found that I could memorize whatever it is better than needing a mnemonic. But every so often, things I would forget whether this or this, so I'd do a little quickie mnemonic to do it. So mnemonics are very helpful. I'm not against them. I think they could be very helpful. But anyway, so back where we were. So we're talking about these coenzymes. The coenzymes are vitamins.
Yeah.
And I'll tell you the two main ones that we're going to be talking about. Why a vitamin? What's the deal with vitamin? The word vitamin is something that we need preformed in our diet, right? Meaning we can't make it ourselves. Originally, when they were coming up with that word 100 and some odd years
Vital
ago,
minerals.
they realized that the molecules that they discovered that we needed preformed were amines. Remember the word amine? I told you about an amine. It means it has a nitrogen in it. And so they named these things because we had to have them in our diet. We couldn't make them. They called them vital amines. And then when they realized that not all the things that we need to preform are amines, they changed it. They took off the L, took off the E, and just called them vitamins. Or in Britain, it's vitamin. They'll say vitamins today.
Yeah.
But anyway, and by the way, just for your knowledge,
So funny.
for historical reasons, there's one molecule that's called a vitamin that isn't a vitamin. It's a hormone. It's vitamin D. It's actually a hormone, not a vitamin.
Yeah.
But for historical reasons, they thought it was a vitamin. The only way you get vitamin D in your diet, if it's not artificially put in, which it is now, would be if you ate fish livers, and the Inuit people live way. The Eskimos who live really far up and don't get exposed to much sunlight for half a year. They ate the entire fish, so they would get enough. The fish would store the hormone in its liver, so if they ate the entire fish, and they'd get it. When I was a little kid, I ate fish. I remember eating some cod liver a lot, and I actually learned to like it. And then, God, years later, when I was in college, I had some friends that they were a kid, and I went into the refrigerator to get a Coca-Cola, and they said, "Hey, there's a little bottle of cod liver oil." I was like, God, I used to like that as a little kid. So I said, can I just try it, see what it tastes like? Oh, God, it was horrible. It was horrible, fishy stuff. Awful. But when I was a little kid, that was the thing. They give you cod liver oil. Nowadays, what they do is they put the precursor to vitamin D into milk products because the main function of vitamin, it has more than this function now. That's something they've learned. But one of the main functions in vitamin D is so you can absorb calcium. And we live far enough north that we don't get enough exposure to the sun to make our own hormone that we call vitamin D. Because we make the precursor to it. We need the UV light shining on the skin to convert it to the active form. But at 6 months a year, we don't get enough sunlight. So they put it in milk products, and there's a lot of calcium in milk. And that way you absorb it. You get to absorb it. So that's a good thing. I think it's a good thing they put it in there. So then if you're eating milk products, during the winter months, you should be getting enough. And actually, they recommend now that you take a supplement for vitamin D. And I think it's actually a wise thing. At least 6 months a year to take a supplement. It's a wise thing because they found receptors for vitamin D on all kinds of cells, including your immune system cells, your nervous system. So it's not just for absorbing calcium. It's for other things too. So it's a very
don't.
Anyway, those are questions.
Which one do we get from the sun?
The vitamin D that they fortify things with,
Yeah.
where do they get that from?
I don't know. I'm not sure, actually. Good question. But it is, by the way, vitamin D is a steroid hormone. It's not a vitamin, it's a steroid hormone, just like the sex hormones. Cholesterol is the basic unit, and they may just make it artificial. Because it's not that hard to make artificially. They just take the cholesterol molecule, put certain things on it. The organic chemistry people are pretty good at this stuff, Anyway, back to these coenzymes, or vitamins. One of them is, the one we're going to talk about, let me say the main one. The main one we can talk about is called NADH, NAD plus. Okay, NAD plus. Okay. Nicotinamide adenine dinucleotide. You don't need to know about this, but niacin would be the vitamin. Okay, but it's got this long, involved name. Okay, but this molecule can combine with 2 electrons and only 1 hydrogen ion, and it makes what's called NADH. And so if you have a reaction where electrons and hydrogens are given off, NAD might be able to accept them, forming NADH. So this would be the oxidized form This is the oxidized form. And this is the reduced form. But then later, maybe the next reaction, NADH can then give its electrons, its 2 electrons and its hydrogen ion to somebody else. So in other words, it's just a carrier. It's just a carrier. It can give it up. It can give the electrons away. And we're going to see why this is important because look at this thing down here. Electron transport system. We're going to see how important that system is. So it's all building up to what is really important stuff. So oxidation reduction reactions. Oxidation, loss of electrons. Reduction, gain of electrons. But in our cells, who's good at doing this? These coenzymes that we get preformed in our diet with certain vitamins. And the main one is that I'm showing you is that. So if you just understand there is this molecule, whatever the letters stand for, called NAD plus, and if it gains 2 electrons and 1 hydrogen, it's converted into NADH. That's it accepted electrons. It can give it off, these off to someone else in another reaction. Yeah.
So oxidation and reduction work together like the catabolism and anabolism, like they
Yeah, except even closer together because they have to have the exact same problem.
Okay.
Catabolic reactions can happen now.
And store
ATP,
store the energy and then
an hour
release
later.
Yeah.
But these happen immediately. So in other words, where these guys, they weren't just sitting there waiting. They were actually handed to him by someone else that I don't have in my reaction. And in this reaction, hey, they have actually handed these to somebody else. I just don't have that in my food.
So they're delivery boys?
Say it again?
They're like a delivery.
And so, you know, they're a carrier.
Yeah, they deliver
They're
stuff.
taking electrons from one molecule here
Yeah.
by doing this and then handing
And
them
then
off
off,
to someone else.
just like the high energy bonds, just
So-
faster.
So it's,
Okay,
just
got it.
it's a carrier. Right? There are a lot of molecules that are carriers of whatever it might be. In this case, it's carrier of electrons. All right, now why are we getting into this? Let's talk about some of these things. Let's do this glycolysis so we have some understanding of that. Glycolysis. Glyco just means sugar. Lysis means breakdown.
All right.
All it means. So, glycolysis. So the glyco part, the glyco just comes from the word meaning sugar. The lysis comes from the word meaning breakdown. So again, what I want you to think about in terms of energy, you know, is that you have in your cells glucose, for example, sugar. That's the main energy source in your cells. You know, your main energy source when you're eating, cereal or putting in your coffee, that's sucrose. That's a combination I mentioned to you once before. It's a combination of glucose and fructose hooked together. In your cells, they just break in your stomach, actually, the small intestine. It just breaks the sucrose into the glucose and fructose. You absorb those and use them for energy. Fine. So this is the breakdown of sugar, or specifically we'll say glucose. But see, your cells can either convert glucose to fructose, so it's easy. So sugar is a molecule with all kinds of chemical bonds, right? All kinds of covalent bonds are formed. Who made that sugar? Well, enzymes were involved in the process, absolutely. Plants, plants made them, okay? And then we eat the plant, or we eat something else, you know. And of course, it took energy to make the sugars. Where did that energy eventually come from? Ultimately, the sun. Okay, so just to keep this in mind, or all right. But here's the deal: glucose, by the way, is a 6-carbon sugar. And it's going to go through a series of reactions. And I'm not going to worry about the reactions. I mean, you know, that's the thing. A lot of times in these classes, I want you to memorize the glycolytic cycle. No, I'm not going to have to do that. I want you to understand what's happening. Sugar breakdown, but it's not a complete breakdown in glycolysis. This is a partial breakdown. And you're going to break it down into 2 pyruvic acid molecules and 2 ATP are formed. And each pyruvic acid molecule is a 3-carbon molecule.
And that's the breakdown of sugar.
This is glycolysis. Now notice we haven't totally broken it down. We've only broken it down from a 6-carbon sugar to 2 3-carbon. Well, it's not really it's an acid. It's not sugar, but whatever. 2 3-carbon molecules. So we haven't broken it down very far, have we? We basically split it is all that we've done. We did get some energy out of it, some usable energy in the form of ATP, right? We did trap some of that energy that was given. Larva came off the seed, so we did trap some of it by making ATP.
So that's glucose. That's the 6-carbon sugar.
Yes,
right?
glucose. Oh, I'm sorry, I didn't put that down. You're absolutely right. Sorry. Glucose. By the way, fructose is a 6-carbon sugar, same chemical formula.
Okay.
Yeah, glucose, 6-carbon sugar. So what we've done, so I should have had it up here. So I should. Hey, look what I did. Let's do this. I should have done this. That's what I meant to do. I went step. There's several steps involved. We don't care what the steps are. But glucose, which is a 6-carbon sugar, is broken down into 2 3-carbon molecules, and 2 ATPs are made. There's not very many ATP left, right? There's 2 left. But whatever. 2 more than we had a few seconds ago. By the way, was any oxygen involved in this process? No. And so this is said to be an anaerobic process. Anaerobic process. What does that mean? It just means no oxygen is involved. The word means without air, but what they're really talking about is oxygen. An anaerobic process, and that means no oxygen is used. No O2 used. Okay. And it takes place in cytoplasm. So this is just something you should have in your notes in your mind and the test on next Wednesday. Okay? Anaerobic process. You will see textbooks. I think actually your lab manual says this. And it was supposed to be corrected, but it might not be corrected. But you will see textbooks and they'll call it anaerobic, they'll call it glycolysis, anaerobic respiration. Wrong. Absolutely, totally, completely wrong. And so several textbooks that have said this, I have written to them to tell them they are wrong. Now, textbook authors don't like people to write to them and tell them they're wrong, and usually they don't bother to write back.
So, yeah, tell them
and
they're
if they do write back, I will then explain. I usually explain why they're wrong in the first place, and I give it. But if they write back, I give them references and all that kind of stuff, and then they never write back again. And although one book did say that they will change it in the next edition, but the other book just ignored me. But here's the problem: it's not a big deal. It's totally not a big deal for your purposes, or even for my purposes, but for purposes of being accurate. And there is such a thing as anaerobic respiration. But only a few bacteria can do that. Only a couple of bacteria. Most biologists don't know anything about bacteria. There's only microbiologists that know about that. And I happen to study this stuff because I like all these little microbes and stuff like that. So I know about this stuff. So I give them references and try to explain what the difference between anaerobic respiration versus an anaerobic process. They ignore me. It's okay. It's all right. I've been ignored before, so it's not. But anyway, so if you do read that and you see glycolysis and anaerobic respiration, oops, wrong. It's just saying no, it's not a respiration. It's a. We are going to talk about respiration. That's an important process. This is just not a respiration. It is anaerobic though. All right. Let me tell you a little bit about fermentation before we get into respiration. Fermentation. Well, let's start. Most organisms on Earth can break down sugar in this way, with glycolysis. Almost the same processes that our cells use and plant cells use and bacteria, fungi. Most organisms on Earth use that exact same process to to break down sugar, which I think is kind of cool. The fact that that is the case, because that just shows how interrelated we all are. You know, this isn't just a chance thing; we all do it. Anyway, but here's the point: what happens when you get to pyruvic acid? And that's what makes organisms different from each other. Okay, so I'm going to say here, most organisms on Earth perform glycolysis. In other words, they all like chocolate, or rather sugar, glucose, sorry, glucose. They all like glucose, okay? Perform glycolysis. But what happens to the pyruvic acids?
I don't know.
And the answer is that's what makes one organism different from another. I'm going to say it depends upon the organism. Okay. So I said most organisms on Earth perform glycolysis, but what happens to the pyruvic acids? I said depends on the organism. If you are a yeast, and you're going to be used to make bread or make wine or make beer or something like that, then you'll do what they call alcoholic fermentation. If you're and I'll write this up, but if you are a little bacterium called a lactic acid bacterium, then you can make lactic acid, and you can make from that you might be able to make some cheese. We'll talk about that more briefly. If you are an aerobic organism, and by the way, yeasts are aerobic, so they can do what I'm going to talk about, but if you don't give them air, you don't give them oxygen, then they'll do what I just said. I'm going to write it down. But if you are an aerobic organism, all eukaryotic organisms are aerobic. Some bacteria are aerobic. Then you will do what they call cellular respiration. So let me write this up. So I'll put if the organism is aerobic, parentheses, all eukaryotic organisms and some prokaryotic organisms. If the organism is aerobic, then cellular respiration occurs. And it's going to occur in a little membrane-bound organelle that all eukaryotic organisms have. And that organelle is the mitochondria, they call the so-called powerhouse of the cell. Okay, then cellular respiration occurs. In mitochondria, if a eukaryotic organism so that's what we're going to be talking about the mitochondria in a few minutes. So if it's a eukaryotic organism, such as a plant or an animal or a fungus or something like that, then they will do this so-called cellular respiration. If you're a bacterium that can do aerobic metabolism, and there are some, they will do similar kind of thing to what we're going to talk about. They just don't have mitochondria. We'll come back to it.
So what are the final products of glycolysis?
That's it, right there. Those two guys right there.
Oh,
That's it.
2 pyruvic acids and 2 ATPs.
Two ATPs. Those are the final
They're
products.
each 3 carbon molecules. That's what I forgot to
Yeah,
ask.
each is a
3 carbon sugars.
Yeah. So it's not really a sugar. It's an
Just-
acid. So
okay.
but each each is a 3-carbon. They're, you know, so the 2, 3. So you get these 2 3-carbon molecules. So you just took a 6-carbon molecule, broke it into 2 3-carbon molecules.
Okay.
It was a little more difficult than that because there are a lot of steps in the process. But we're not worrying about all the steps. Just you start with the 6-carbon sugar, you break it down into these 2 3-carbon molecules, and you get a gain of 2 ATPs. 2 ATPs more than you have to give them. That's not very much, and we'll see that when we do cellular respiration, we get a lot more. I mean, a lot more. But we're not there yet. But anyway, so let's go back here. So this is if you're aerobic. What if you're not aerobic? If you're not aerobic, such as most bacteria, you probably do fermentation. So let me read that fermentation. So that's the if you're. This is if you're aerobic. That's this part. The next thing is if not aerobic. Not aerobic. Most prokaryotic. Remember, prokaryotic are the bacteria, right?
Mm-hmm.
Most prokaryotic organisms. And some eukaryotic, if there's not enough oxygen around. And this is the example I'm going to give you with yeast. Yeast molecules are fungi, the fungus. Yeast are little fungi, so they're eukaryotic. But if you're making bread or wine or something like that, you don't give them enough oxygen, they'll do the fermentation with not enough. So if not aerobic, then they perform fermentation. A fermentation. So let's talk. What is fermentation? Fermentation. So everything's starting with glycolysis. Okay, we're still starting with glycolysis. So this is the beginning. Starting with glycolysis, you get the pyruvic acid. So what you're doing with the pyruvic acids depends upon whether you are, aerobic or not aerobic. Anaerobic. If not aerobic, okay, then you do a fermentation. So the fermentation is you don't get any more ATP than you already got, but you change whatever that pyruvic acid. Pyruvic acid is a fermentation. Pyruvic acid is converted to some waste product. Depends upon the organism. We'll talk about this. I'll give you 2 examples. But no more ATP formed. So how many ATP have we formed so far? From 1 glucose, we formed 2, right? From 1 glucose, we got 2 ATP. So I'm saying whatever's happening in the fermentation, we're not going to get any more ATP. All we're doing is making some waste product. In other words, pyruvic acid isn't the waste product. We have to convert it to something else. So I'll give you 2 examples of fermentation. I'll do this one here. So here's 2 examples. And there are a lot of
Erase it all. I got it right
There's
here.
actually dozens and dozens. I don't know how many known fermentations there are.
I'm just doing this to stay awake.
We don't need to worry about all that. That's only if you are want to be a microbial biochemist, then you'll learn all these things. But most of you don't want to be microbial biochemists, I'm sure. But anyway, so here's 2 examples of fermentations. Keeping in mind there are dozens and dozens of other examples. 2 examples of fermentation. Okay. 1, alcoholic fermentation. I know, you know what an alcoholic is, but that's not, we're not talking about a person. It means forming alcohol. So what happens there is it's the two pyruvic acids, each pyruvic acid is converted into one alcohol molecule, ethyl alcohol, plus one CO2. And ethyl alcohol is a 2-carbon molecule.
So each of the pyruvic acid turns into one of those?
So each pyruvic acid, we have just 2 for every glucose, but each pyruvic acid gets turned into one alcohol molecule and one CO2 molecule. So pyruvic acid is 3-carbon, right? Alcohol 2-carbon, CO2 1-carbon, so that's the 3 carbon. Yeah.
So if you had the 2 pyruvic acids that are part of the glucose and broken down, you get 2 ethyl alcohols and 2 glucose.
Yes, you get 2. Yes, exactly. You get 2 of each. Yes. By the way, there are a lot of different alcohols. I think I mentioned this to you. The ethyl alcohol is the kind we can drink. As long as you drink it in moderation, you're fine. But this is the alcohol you use that is made. This is the alcohol that is made when you're making beer or wine. And if you're making like wine, you put the grape juice in with the yeast, and then it starts bubbling. I talked about this way back when I was talking about fermentation and making wines, and the French wines were getting disease. They didn't know why. But what's happening, of course, is the bubbling. The bubbling is the CO2 coming on. And the alcohol is what is what you have in the product that you want or you like. But we use the exact same yeast with the exact same process to make bread. You take the same yeast, brewer's yeast. You can get that from a place where they make beer, and you put that in your bread, and you mix it with you have some sugar, and the yeast are doing this is all done by yeast. Some bacteria can do this, but we use yeast usually. But when you're making bread, there's alcohol and CO2, and the CO2 is trapped in the little pockets, and it causes the bread to rise. That's what we're talking about, letting the bread rise. It's just making CO2. When you bake the bread, you burn off the alcohol, so there's no alcohol left in the bread. If you smell it when it's rising, you can actually smell some alcohol. But that all bakes off. So when you're making bread, you want the CO2. When you're making beer or wine, you want the alcohol. They're both being made. Question, I saw a hand.
Well, I just want to talk about carbonation, and
that's even more.
So is all carbonation just the CO2?
CO2, yeah, that's the CO2.
That's-
Well, for beer, do they add more? For carbonated drinks, like soft drinks, they add more CO2. They just pump CO2 in.
Yeah.
But for beer, that's probably the natural carbonation. I know in Champagne, they do a second fermentation. They do a first fermentation. Then they take a second fermentation with a different kind of yeast. They add some extra sugar. Then they cork it, and then they don't let the CO2 just go out in the atmosphere. They keep it trapped in the bottle, and that's why when you open the bottle, it bubbles out. But anyway, so the other kind of fermentation is lactic acid. These are only just 2 of hundreds of examples. Lactic acid fermentation. And what happens there is each pyruvic acid is converted into lactic acid. And by the way, these are both 3-carbon molecules. We haven't lost any, nothing comes out for like CO2, it's just a 3-carbon molecule. This is used when we make cheese. You actually take the bacteria that do lactic acid fermentation, or if you're making, it not be cheese, it could be yogurt or whatever. But and if you look in those things, you'll see lactobacillus and all these things. But these are doing a lactic acid fermentation. For example, if you're making cheese, the bacterium will convert glucose into lactic acid. The lactic acid is the waste product. The acid causes change in the structure of the protein, the milk protein, the casein. It comes out as curds. You pack them together and you let it age, and then we call it cheese. So this is how we make cheese. By the way, when you exercise strenuously, we do the same thing. One last thing. So I didn't get to any of this last stuff that I got a lot to do, but one last thing we say about fermentation. Write this down, and then the test will end here. On Monday, I will continue with this. but it won't be on this test, it'll be on the next test. But this is, the next stuff's tricky enough. But last thing about fermentation. So in a fermentation, let's say a fermentation, let's do this. This is the one last important part here. And then we're quit, right? We've done fermentation, we're almost done. Fermentation is the partial breakdown of sugar with some organic molecules left over. With some organic molecules as a waste product. Write this down and let's look at it for a second. Don't just go just a second. It's important for you to see this. So fermentation, a definition of fermentation would be a partial breakdown of sugar with some, I have some twice, don't I? With some organic molecules as waste products. Now look at, and then write that down and then look at the examples I gave you. With the alcoholic fermentation. CO2 is a waste product, but that's not organic, remember? But alcohol, that's still, that's an organic molecule. We can drink alcohol and we can get some energy out of it. For the organism that gave this off, it's a waste product. They can't use it. But we can actually use it. Lactic acid, recarbonate acid. There's still energy available in those molecules. And we make some actually when we strenuously exercise. Yeah.
Do you know why? I mean, sugar has 4 calories
per gram. That's per gram. Wait.
Alcohol has 4. It has 7.
Per gram of alcohol? Are you sure? Per gram? I have to look. But it's a smaller molecule. It's a smaller molecule. So you have more molecules. You have more molecules per gram. It may be, but you have more molecules per gram because it's a small molecule. It's only 2 carbons versus the 6.
Really?
Oh, so that's probably why it has
Yeah, I think so. Oh, sorry. Yeah, I think so. Yeah. I think that's probably why. Okay. So keep in mind that the exam will go through this fermentation. This. On Mondays, I said I will continue, but it won't be on the exam. It's kind of tricky stuff, but I want to talk about mitochondria. By the way, in contrast, when we talk about cellular respiration, no organic molecules, only as waste products, only CO2. CO2 and water will be the waste product. In other words, if you're an aerobic organism, you're going to burn sugar all the way to CO2 and water. We'll see that on Monday. Okay? That's it for this exam. Not that.
This Friday, there's going to be a study session?
Yes, it's right.
All right.
Yes. Here.
My emails
Oh, that sucks. No!
Are you okay? Are you okay? And I'm like, I'm okay. So everything. Anyway, so everything's fine. I don't know. You know what? Leave me alone. I'm good. I'm gonna go to the salon.
Yeah, it's right here. Same thing, same time.
Oh, come on. Why are you giving me hell?